again. Today I would like to explain a little bit about our motivation on doing research on lines. I recorded this video 14 months ago. I recorded it last autumn and now it is December 2025. I didn't have much time to edit or do anything. But in the meantime, actually, so this video is about two articles. One takes care of the classical cases and one takes care of some exceptional cases. It takes care of minuscule geometries and hexagonic geometries. So in the meantime, the article about the classical cases was already published in the journal Discrete Mathematics. And the other article is finished. We have not submitted it yet or uploaded it anywhere because I wanted to still proofread it one more time. But I was so busy with writing my thesis that I didn't have the time yet. But our results for the exceptional cases are also ready now. So I had to now today re-record the main results because we have more now. And yeah, some of them are already published. But yeah, now you will hear my past me from 14 months ago speak. At the time I was on a research stay in Ghent in Belgium, so it's also a different apartment. The sound there was very bad. In the meantime I got a microphone, but I couldn't find it today. So what I record today is also without microphone, but in the meantime I just can't find it. I will find it. For next time I record something, I will have the microphone, okay? So this video, the sound, I know it's quite bad, but let's just focus on the content. So, you know, I made this video about opposition and lines in parapolar spaces of type E6, and one could ask, why do we even need that? Why are we interested in that? And today I would like to explain that, but also we are writing two articles where we characterize lines in finitely incident geometries. One article is already on arXiv, it's about the classical case, and then we're also doing the exceptional case, and we're still writing on the article at the moment. And I would just like to explain why we are doing that. So now actually forget about lines for a moment. I want to tell a story. And like all good stories, the story starts with Jacques Tits. Jacques Tits showed that given a spherical buildings and two elements of the same type, we can always find an element that is opposite to both of them. This theorem will be the protagonist of our story. And now in this video I will define buildings a little bit differently than I have in previous ones and also probably than I will do in future ones. But I will tell you about that now. So in this video we will only focus on spherical buildings and we will view buildings as simplicial complexes with certain properties. And I will tell you which properties, but first, just that you can get an idea, the buildings we will be talking about will consist of glued together triangulated spheres. And these will be called apartments. So an apartment in a spherical building is just a triangulated sphere, and we want to glue several of them together following certain rules, and that is visually, roughly, what our buildings will be. I will assume that we are all familiar with simplicial complexes. And now a simplicial complex will be called thick if every codimension 1 simplex is the face of at least 3 maximal simplices. And a simplicial complex will be called thin if every codimension 1 simplex is the face of exactly 2 maximal simplices. Note that there can exist simplicial complexes which are neither thick nor thin. So in this video we will define a building as follows. A building will be a thick simplicial chamber complex. That means that all maximal simplices have the same dimension and we can always find a gallery between maximal simplices. That means that the maximal simplices lie together in a way such that if we have 2, there are other ones that all intersect in the codimension 1 simplex, such as we can basically go from one maximal simplex to the next, to the next, to the next, until we reach the one that we want by crossing through codimension 1 simplices. this is all just like a rough thing because we don't need to understand buildings in detail for this video. So a building will be a thick simplicial chamber complex such that it is the union of thin simplicial chamber complexes, and these we will call apartments. So a building is a union of apartments such that for every two simplices in our building we can always find an apartment that contains both of them, and such that all apartments are isomorphic through an isomorphism that fixes every vertex in the intersection of the two apartments. In the context of buildings, we also call maximal simplices chambers, and the codimension 1 simplices we also call panels. To understand the result by Jack Tits a little bit better, we still have to understand what opposite means. And for that, we will first look in an apartment, and then we will define it for the building. So, take an apartment. As mentioned before, the apartments are triangulated spheres. And if you take a vertex in a sphere, then what is opposite is just the vertex on the other side. So it's what one would expect. I'm not formal about this at all. I will only describe it such that you can visualize, but I'm not formal about this. So, how it is described in the literature is with walls. So, if you take a sphere and you cut it in two halves, but imagine that you don't obtain two clean halves, but two halves that intersect in something. So we have a cut, and then where these two halves intersect, and this intersection is then also called a wall. And one would say that two vertices in an apartment are opposite if they are always contained in the same walls. That means no matter how we cut the apartment in two halves, either both vertices are always in the wall or both are not in the wall. And that is what it means for vertices to be opposite in an apartment. Now let A and B be two simplices. Then we say A and B are opposite in an apartment if the union A and B is close under opposition. If we take a chamber in an apartment, then the opposite of a chamber is unique. And now the thing is, one can show that if two simplices are opposite in one apartment of the building, then they are opposite in all apartments of the building that contain these two simplices. Hence, we can say if we have two simplices that are opposite in an apartment, that they are opposite in the building. And that is how we define it for simplices to be opposite in the building. So now we know what a building is, we know what opposite means. That means we have all the words to understand our protagonist a little bit better. To remind you of one thing, because we defined buildings as thick simplicial complexes, we know that in a building, each panel is the face of at least 3 chambers. And now 3 is some number, but let's just define that a building has thickness at least t if every panel is the face of at least t chambers. Because why should we only care about 3, right? And now we could ask our protagonist, do you also work for thickness at least t plus 1? So the phrasing would then be, in a building of thickness at least t plus 1, given t different elements of the same type, can we always find an element in our building that is opposite to all of those? And the answer to that question is yes, we can do that. And the proof works in the exact same way. So basically, Jack Tits proved that, because it's just the same proof. Maybe you have to add one sentence at the end, but it's the same proof. But if you want to see the proof for this more general result, I guess, you can look in our article. So the article joint work with Hendrik from Maldeghem and Jeroen Schillewaert, and there we wrote down the proof for that. So that was maybe a little bit too easy, but now we can ask, in a building of thickness at least t plus 1, given t plus 1 different elements of the same type, can we still find an element that is opposite to all of those? And to answer this question, we have to think a little bit more. So a little fun fact, spherical buildings of rank at least 3 are classified, and we have buildings of type AN, BN, CN, DN, E6, E7, E8, F4, and buildings of type AN correspond to projective spaces. The buildings of type BN and CN correspond to thick polar spaces. Buildings of type DN correspond to thin polar spaces, and for the rest we get parapolar spaces. And now we will look at the example of a projective space, because I assume that most people are familiar with projective spaces, but maybe not with polar spaces or parapolar spaces. So if we now phrase our question for projective spaces, the question would be, in a projective space of dimension n, in which every line has t plus 1 points, given t plus 1 different k-dimensional subspaces, can we always find a subspace that is opposite to all of those? So for a projective space we have the AN diagram, and we can look at the opposition map to see what does opposite what. And we can see that points are opposite maximal singular subspaces. Now let's look at the easiest example of a projective space, which is the projective plane. Let's take the easiest example of a projective plane, which is the Fano plane. In the Fano plane, every line has exactly 3 points. Now the question is, given any 3 points in the Fano plane, can we always find a line that is opposite to all of these points? Which just means the line should not contain any of these points. And the answer to the question is no. Imagine the 3 points being on a line together. Since in a projective plane all lines intersect, it will be impossible to find a line that is opposite to all of these points. So in general we have to say, no, we cannot always find such an opposite. So in a building of thickness at least t plus 1, given t plus 1 elements, can we always find an opposite? In general, no, because we already have one counterexample. And then of course we could ask, okay, so then when can we find an opposite? When can we not find an opposite? But then if we can already see, it might be a bit complicated to prove anything there, we should maybe first ask the question whether or not we actually want to answer that question, right? Is it worth it? Do we really want to put time and effort into this? Maybe we don't really need it anyway. So maybe if we don't find this question interesting in and of itself, we may find it interesting to determine all of the Levi subgroups of parabolic subgroups of groups of Lie type related to spherical buildings. And maybe we may also find it interesting to determine all the special and general groups of projectivities of irreducible residues of those buildings. And actually, if we determine all of these projectivity groups, then we also determine the Levi groups. So maybe we want to do that, right? Maybe we want to do that. But maybe then first we want to understand what a projectivity group is. So I told you what it means for simplices to be opposite in an apartment, right? Now let's take 2 non-maximal opposite simplices, f and f prime. Then these will be contained in some chambers, right? Let's say we have a chamber here that is called C, C containing F. Then there exists a unique chamber containing F prime that is closest to C. And this is how we define a projection. And this induces an isomorphism on the residue of a simplex. So all the chambers that contain the simplex F form a thing that is also called the residue. And we, by mapping, like I described, we get this isomorphism from the residue to the other residue. And if we are in our large building and not just in an apartment, we can maybe have a simplex F naught given, and then a simplex F1, F2, F3, and F3 should also be opposite F naught, and f2 is opposite to f1 and to f3. And then we can go from the residue of f0, project to the residue of f1, to the residue of f2, f3, and then back to f0. And if we have a product of such projections, we also sometimes call it a projectivity. And if we start and end in the same residue, it is called a self-projectivity. And if the projectivity, the self-projectivity that we are given, is a product of an even number of projections, then we call it an even self-projectivity. And now the group generated by all self-projectivities of a simplex is called the general projectivity group of that simplex, and the group generated by all the even self-projectivities of a simplex is called the special projectivity group of that simplex. So I said maybe we would find it interesting to determine all of these projectivity groups, and then also this gives us the Levi subgroups of parabolic subgroups of groups of Lie type, blah blah blah. And fun fact, Hendrik from Maldeghem, Jeroen, Schillewaert and me, we have already determined all of the special and general projectivity groups for irreducible residues, for spherical buildings of rank at least 3 and simply less type. Rank 2 was already done by Norbert Knarr a long time ago, but we did it now for rank greater equal 3. But only so far for the simply laced case, and we have put all our results in a nice table, so you can look up the article if you want. But yeah, so we determined all of these groups. That was one project that we had. So now it might be interesting to understand how we managed to determine these projectivity groups. Maybe have there been certain tools that we used that made it a little bit easier. And I mean, there were many different tools that we used, but one tool in particular I found very, very nice, and I will talk about it now. So it is the case that in certain situations the general group of projectivities is the same as the group generated by projectivities of length 3. And then of course if you want to determine these groups, it might be much easier to look at what the projectivities of length 3 generate and not what in general all the projectivities generate. And that is a tool that we wanted to use and that we also used, but then of course you have to know when is it the case that the general group is already the same as the group generated by the projectivities of length 3. So let's say we are in a sufficiently nice situation. I will now tell you a little bit about how in such a good situation we can break up a projectivity into projectivities of length 3. So first we need some projectivity, and let's say we have 4 non-maximal simplices, f0, f1, f2, f3, such that f0 is opposite to f1 and f3, f1 is opposite to f2 as well, and then f2 is also opposite to f3, such that we can go from or project from the residue of f0 to f1, f2, f3 and back to f0. So this is our projectivity, and now we want to see how we can break it up into projectivities of length 3. Imagine we can find a simplex that is opposite to all of them. Then we can picture first our given projectivity that would go from here to here to here to here and back. And now if we can find a simplex that is opposite to all of them, we can also, instead of going from here to here, we could go from here to here to here to here to here and then to here, because this simplex that is opposite to all of them, call it G. The projection of f0 onto G is something that is closest, right? And then if you project to the residue of f1, we get something that is closest to what we had here. And then if we go back, of course, since this is the image from this thing, we go back to this exact thing. And because this was the image of this thing, we go back to exactly this thing. So this doesn't change anything. We can just do this, and it's the same as going from here to here. And this we can then use to write our projectivity in a different way, such that we can always see triangles. And I will read off how exactly, because it's quite long. So instead of looking at going from F0 to F1 to F2 to F3, we can go from F0 to G to F1 to G to F0 to F1 to G to F0 to G to F2 to G to F1 to F2 to G to F0 to G to F3 to G to F2 to F3 to G to F0 to G to F3. If we do it like that, then we already get that the projectivity from F0 to F1 to F2 to F3, we wrote it now as a product of three projectivities of length 3 and a projectivity of length 2. But we can then go on like that and then prove at the end that for any given projectivity we can always write it as a product of projectivities of length 3. And I mean, we have a whole proof for that that I will not explain in detail right now. But the idea is, take a projectivity, find some simplex that is opposite to a bunch of them, and then we can make these triangles, and these triangles are just projectivities of length 3. And this is how we break it up if we are in a situation that is nice enough, such that we are allowed to do this procedure. As I said, that is only possible in certain situations. Of course, one condition we already mentioned, we have to find a simplex that is opposite all of the other simplices. But this is not the only condition. And now, of course, it became obvious what this whole projectivity stuff has to do with our original question, because we just saw we need to find a simplex that is opposite a number of given simplices, right? So now one can see the connection to the beginning, I guess. So you remember where we left off? We were wondering about the question whether or not we want to answer this other question. And now we found out, yes, we do want to answer this question, because if we answer this question, sometimes we can do this nice reduction with the triangles or quadrangles or whatever, and then we can determine the projectivity groups. And when we can determine all the projectivity groups, then we have the Levi subgroups. And maybe that is very nice, because maybe we want to do group theory or something like that. But we also already found out that it's not always the case that given t plus 1 elements that we can always find an opposite. We already found out that it's not always possible. So now the question becomes, can we classify all counterexamples maybe? But then if we ask this question and we answer that question, how can we view our results? How can we interpret our results? Maybe we can also take different viewpoints and see what this looks like then. So actually for projective spaces there is a notion called a blocking set that was already there. We didn't come up with that. So there's a notion of a blocking set. What is a blocking set? A blocking set in a projective space is a set of points such that each hyperplane contains at least one point of the set. And now if we think about our question, for example, I told you in the projective spaces we asked, given t plus 1 different points, when can we not find a maximal singular subspace that is opposite to all of them, right? And now if we don't only answer our question for projective spaces, but do it in general for spherical buildings, then this gives us a way maybe to investigate analogs of blocking sets in general Lie incidence geometries, and that could be quite interesting. There's also this phenomenon that sometimes you have a Lie incidence geometry and the points of the geometry are all points of, for example, a projective space, but then not all the lines are contained in this geometry. I have an example. Take a symplectic generalized quadrangle. Then the points of that quadrangle are all points of a projective space PG3K. But the lines are only the totally isotropic lines of the projective space with respect to the symplectic form. And the other lines in the projective space also contain points of the quadrangle but are not lines of the quadrangle. And there's an article by Hendrik from Maldeghem and Kazikova where they try to capture this phenomenon of pseudo lines, but they called it geometric lines. So a geometric line is a set of points such that each object of opposite type is either opposite none or all except one point of that set. And now I will tell you about some of our results, and then maybe it will make a little bit clearer how this all ties together. In a finite classical geometry, in which every line has exactly s+1 points, any set of at most s+1 points which does not admit a common opposite is either a line, a hyperbolic line in a symplectic residue, or an ovoid in a proper ideal symplectic subquadrangle in characteristic 2 in a residue. Just a short description of hyperbolic line. So we said we cannot find an opposite if the set of things that we want to find an opposite to is a hyperbolic line in a symplectic residue. Symplectic residue means we have a sub-building that corresponds to a polar space, a symplectic polar space. So imagine we are in a polar space. What is a hyperbolic line? Well, first we take two opposite points, and then we look at all the points that are collinear to both of them. And then we get a set of points. And then we look at, for these points again, what are all the points that are collinear to all of these points. Of course, this new set then includes the 2 points that we started with, but could also include some more points. And then this new set, this is a hyperbolic line. This is how it's defined. So you start with 2 opposite points, look at all the points that are collinear to both. This is a new set of points, and then we again want a new set of points, and that we obtain by looking at, for the new set of points, looking at all the points that are collinear to all of those. And that is a new set of points. It's easier to see in a picture. Just to make that a little bit clearer, geometric lines are either ordinary lines or hyperbolic lines with enough points. I will not explain that in detail now. It might be a little bit confusing now that I introduce like several different concepts, but I will refer to the article for more information. If in a thick, irreducible, spherical, finite classical building delta of type xn, where n is greater or equal to 3, the panels of cotype I are s thick and s is odd, then a set T of vertices of type I is a geometric line in the I-Grossmanian geometry if and only if it has size s+1 and admits no common opposite vertex. If s+1 is even, then a set of at most s+1 points is a geometric line if and only if no object of type opposite a point is opposite to every point of the set. For buildings of exceptional type, we looked at Mufang buildings that either correspond to the incidence geometries that are minuscule geometries, which are the ones of type E61 or E77, or they correspond to hexagonic geometries, which are the ones that have either type E62, E71, E88, F41, F14, G22 or G21. And the main results can be stated rather easily if for a moment we ignore F4 and G2. Basically, we can always find an opposite vertex except if the s+1 vertices form a line in the X and I geometry. For type F4, we again have to pay attention to ovoids and certain subquadrangles, and if our building corresponds to a Cayley split hexagon, we have to pay attention to hyperbolic lines, and if our building is split and we are in characteristic 2, then we have to pay attention to certain imaginary lines. So there are just some special cases that we have to pay attention to. And now regarding geometric lines, we have a very similar result for these exceptional geometries. We have that a geometric line is either a line in that geometry or a hyperbolic line in a simp of that geometry, whenever that simp corresponds to a symplectic polar space, or a hyperbolic line in a split Cayley hexagon, or an imaginary line in the case that we have a Lie incidence geometry of type G22 over a perfect field in characteristic 2 in the split case. So in fact we determined the minimal blocking sets in all of these cases. We found the connection to geometric lines. We generalized the result of Projectivities. We found a great tool to use for our constructions for the Projectivities. We found a tool that might be useful for some other stuff. Part of our results already got published in Discrete Mathematics. So yeah, I think it's quite nice. I will be able to say that I worked on this video for like 15 months or so. I hope you enjoyed it. Thank you very much for watching, and goodbye.